Okay. What kind of variables do we want? Maybe a couple of ints. Int x, int y, int z. Now let's print out those three addresses. If we wanted to print x and y and z out like this, we would be printing their contents. We would see 2, 3, and 4. But let's print out their addresses, which byte they are stored in on the computer. I'm going to copy those three statements. And did you need to break them up onto separate lines like that? No, of course not. I lost my call to system pause. Alrighty, so instead of printing out x, I wonder what the address of this variable is. And some languages do not support this concept at all. Java, you don't care about pointers. C#, pointers are okay, but they kind of straddle the line. They're considered unsafe. And there are other things you should be using rather than pointers. That's C#. C++, you're happy to use pointers. Okay, so there we go. Value 2, 3, and 4 are stored at these three addresses. Those are hexadecimal numbers. We talked about hexadecimal numbers way, way back. AB0, AA4, A98. Notice that they're kind of in reverse order. 98 minus AA4, I wonder what the difference in the spacing of these values are. I'm curious about that, so I'm going to write one more thing. I want to print out the difference between two of these. I'm just kind of curious. What is the difference between the address of x and the address of y? Three. I thought a int was a 32-bit data type, which should have been a difference of 4. Where did it come up with 3? $70 minus 64 is not 3. Oh well. Anyways, forget that. I'm not going to worry about why that didn't give me the answer that I expected. So you see the difference. X is a value, ampersand x is an address. When you declare a variable, you can say that it's not an integer, it's a pointer to an int. Like this. I'm going to declare a pointer to x. Int star px. Why did I use p? Because it's a pointer. Star px is equal to the address of x. I'm going to do the same thing for py and pz. Py is a pointer to an int. I'm curious what the address of y is. Pz is a pointer to an int, and it contains the address of the z variable. I'm going to copy these three statements, the ampersand x, y, and z, and paste them, but change them so that it's px, py, and pz. So they're identical, which makes sense. We got the address of x, we stored it in something called px. So px is a pointer. It gives us the address. What if we actually wanted to change the value of x could we use the pointer to do that? And yeah, we can. But it's not as easy as doing this. We can't just say px, it used to equal 2. What if I wanted to equal a 20? I can't do that. Instead, I have to say that, no, we're actually changing an address. We're changing a pointer. This will let me change the value of the x variable. Now, this is getting a little bit abstract. And if you're not going to go on programming in C++, then it's kind of okay for it to be an abstract concept. But if you are going to be a C or a C++ programmer, you really kind of need to nail this down. It's more important than the 1 or 2 days that we're going to get it in this class. X is a variable containing the value 2. Px is a pointer to that variable. It contains the address of it, 9 million or whatever it is. If we want to change that x from saying 2 to 20, that's the same thing as having that bulletin board. I wanted to change that name Jeff, and I wanted to spell it in some medieval French way with a G-E-O-F-F, I would say, go to that bulletin board, change the first element, here it is. Here's the syntax for it. If this variable is a pointer, this turns it from a pointer to a reference back to that original memory location so that we could change its value or get it out. So now that we've done that, let's print out these 3 addresses. I'm just going to copy and paste again, but put an asterisk in front of each one. It should print out 20, 3, and 4. Px is an address. Star px is the data that that address contains. 20, 3, and 4. So we successfully, I sound like Sean Connery. We successfully changed the x variable's contents from 2 to 20. The addresses didn't change when we did that. If I printed out the addresses again after I do this change, let's do that. Let's move that px is equal to 20 to above these 3 print statements. We'll see that the 3 addresses are the same. It's just the contents that have changed. So even though we changed the value that was stored in that address, it didn't change the value of the pointer. It's still the same address, just like if I re-scribbled on that note card, it's still the same note card. It's still in the same place. It's just got a new value. So pointer variable. A pointer variable is a variable that holds an address, usually just called a pointer. Because a pointer variable holds the address, it points to that data. Just like the address of your house. If you tell me that you live at 123 South Main, is 123 South Main your actual house? No, it's an address to that house. If you tell me to go to 123 South Main, I know where to go, but that address is not the data itself. Your house is the data. 123 South Main is the address where that house is located. We've already seen something that work like arrays, like pointers. Arrays are very, very, very similar to pointers, especially in how they are processed behind the scenes. And that's true in this language, not so true in other languages. Something to try. Something not to try. Forget it. This is showing us that if we have the values 1, 2, 3, 4 in an array, then if we want to print the first one out, we use values sub 0. And then we use values sub 1, and values sub 2, and values sub 3. You can use pointers to step through an array in the same way. There are also things called reference variables, which we're going to skip. Reference variables are something that were added to C++ and they were not in the original C spec. So I'm skipping them and we will go back to them. So pointer variables are another way of using a memory address to work with a piece of data, and I'll show you why you use them. I mean, there's all sorts of reasons for using them. But let's write a function that's supposed to change the value of a variable. Scroll up above main, and let's write a variable called, a function called 0 it, or just 0. And it takes an int as a value, and it sets that variable equal to 0. I'm going to change that x to something else, like the word number. Okay, now down here, after I have created x, I'm going to call 0 and pass x into it. Now you might expect that when we print x out now, maybe just use a cout statement that says x equals arrow arrow x arrow arrow endl, then it might equal 0 now, because after all, something got set to 0. And you can tell by the way I'm setting up that statement that it's not true. X is still going to equal 2 even after this call. X is equal to 2 even though it went into this code and set it equal to 0. If I set a breakpoint here, maybe I can demonstrate why that is. And I really should be making y'all use the debugger as well. Okay, so what I did is I set the breakpoint and then I clicked on debug, and then I have these little choices of whether I'm going to step into, step over. I want to step into this 0 function. If I hover my mouse over x, it says x is equal to 2. It's way smaller than you can see. But right there it says x is equal to 2. That's true. We set it equal to 2. Then I'm going to do step into, which actually steps into this function call. So the arrow is going to jump up there. Step into. Now it's up here. Number is a variable which has a copy of this value. X is equal to 2. It put a copy of it in there. It's just like you made a photocopy of something before you handed it to somebody else to do somebody to do some work with it. So number is a completely separate variable. It is in effect a local variable that gets initialized with the value of this variable. So this is what's known as pass by value or pass by copy. A lot of languages support only pass by copy. There's something else called pass by reference where this actually is the same thing as this. But that's not the way this is working. Parameters, unless you do something very special, are pass by copy. So the value of x gets copied into a new variable called number. You can do whatever you want to that number. Set it equal to 0, set it to 1,000,000, whatever. It does not change x because number is just a copy of it. Just like if I gave you a photocopy of a piece of paper and you tear that photocopy up, I still have the original. It's still equal to 2. But what if we really wanted to be able to change it to 0? That's what you use pointers for. I'm going to just stop the debugging here by clicking that red square, getting rid of my breakpoint. We're going to write a function that actually does change it. Void 0p, 0 at this pointer, I don't know. And instead of merely taking an integer, it's going to accept a pointer to an integer. So int asterisk p number. So star p number is equal to 0. This nomenclature means go to that address that is stored within p number and change it. It doesn't change the value of p number, it changes the value of what p number is pointing to. So if I come down here and I change this 0x to 0px, it's now giving me an error because this parameter is supposed to be a pointer. It's not supposed to be a value of an integer. What could I do to that x to turn it into a pointer? Yeah, I just put the ampersand there. So there we go. I put the ampersand there and I'm good to go. When I print out x now, it will actually be 0. It got changed in here. That is one of two ways that you can get data inside of a function so that where if you change it, that changed value actually changes the original data as well. The other one is references. So there we go. Instead, x is equal to 0 rather than what it was equal to before, which was a 2. So I'm going to add some comments here. This does not change the value of the original data. Just the copy of it stored in the number parameter. This does change the original data because p number points to the address of the original data. And that has a few implications, one of which is that you cannot pass a literal into something accepting a pointer. I could do this, 0, and pass in 100. No problem. That's not a problem because 0 is expecting an integer. We gave it an integer. It's just a literal. It's a named constant. So when this gets changed to 0, it sure did not change the value of 10. But you can't do this. You can't do 0p, the address of the number 10. That syntax just does flat out does not make any sense. So you can't pass in named constants. Something that would be interesting to do, interesting in my mind, what happens if we make x a constant that's not supposed to be able to be changed? This variable is trying, this function is changing the data that's contained within the x variable when it's called like this. I'm passing in a pointer to a constant. Is this going to work? And it says no. Argument of type constant int pointer is incompatible with a parameter type of int. If I had to get this to work, I could come up here and add const here, and that would say, oh, this is a pointer to a constant. Once I do that, it's not letting me change it anymore. Since it's a constant, I'm not supposed to be changing that. So, you know, that's kind of breaking the point of passing it in as a pointer to begin with. Pointers are more low-level than arrays. You are responsible for finding the address and correctly using it. C++ doesn't care whether you use it correctly or not. What do I mean by that? What if I take p number and I add a value to it? P number plus equals 1,000. So I had a memory address, you know, of 9 million. I just changed that memory address to 9,001,000. It's pointing to something that's not even in our program. And then, oh yeah, okay, I want you to write a 0 at that new address. C++ don't care. It's happy to do it. We get an exception. We get an error, access violation. Back in old days, before Windows was a good operating system, it would be happy to let you do it. It wouldn't tell you. You know, kind of like when you write past the end of the array. We compiled it in debug mode, so it's got a lot more information. And Windows itself is supposed to prevent applications from overwriting, you know, each other's memory space. Stop it. Okay. There. So anyways, you know, the compiler has no idea that you're doing something evil here, that you're trying to change data that's not even inside your program. What if we just changed it to 1? We're going to add 1 to it. I don't know. I'm kind of curious as to what happens. It didn't change it to a 0. I wonder what it did change. There's no telling what it changed. Something got changed to 0. Let's pass in C rather than A, because that's C. The difference between A4 and 98 is 6 in my head. No, it's not. I don't know why my brain's not working right. If I wanted to take the difference of those numbers, I definitely did not get the value that I expected. I'm going to, oh, and now I get a runtime check failure. The stack around the variable x was corrupted. So since this was compiled in debug mode, Microsoft added some code to try to catch the fact that you're making errors. I don't want to do that. I don't want errors, so I'm going to go ahead and just not monkey with my pointer like that. It doesn't matter whether you put the spaces before the asterisk, after the asterisk, both. It's treated the same thing. As a matter of fact, I think you can just do this. Take out the spaces before and after the asterisk. It doesn't care. Just like if you do this, A is equal to 1. Doesn't matter whether it's, like that or not. So you can initialize pointer variables with the special value null pointer. I just thought it was null. In C++11, the version that came out in 2011, which might not work on, you're not here, on your implementation, the null pointer keyword was introduced to represent the address 0. You do this if your pointer doesn't have any valid data yet. It's the same thing as setting like x equal to 0 just because you haven't decided to actually put a good value in x yet. The indirection operator. This is known as dereferencing. That dereferences the address stored in int pointer, so that it's actually the contents of the original variable. Here we have a variable called x. We have declared a pointer to a variable, to an int, and put the address of x in it. So if we want to find out what's inside that value, we have to dereference that address. What does dereference mean? It just means the computer's going out to that address to get the actual contents of memory rather than just printing out the address itself. Just like if you wanted to visit my house, you'd have to actually go to that address. You'd have to go to 123 South Main. The relationship between arrays and pointers. That's an array. We have been accessing arrays using subscripts. If you just printed out the name of the array without any subscripts, it would print out the address, just like the pointers print out the address if you print out, the pointer variable. So if we print out vals 0, it prints out the 4, but if we just print out vals itself, whatever memory address in your computer happens to be holding that array, that's what it prints it out. Now they just arbitrarily decide that it's at 4A00, but of course it's completely different on every computer as to where these things are going to get stored. You can use an array name as a pointer. If you want to get that 4 out, instead of using vals subscript 0, you can use asterisk vals. Vals is secretly behind the scenes a pointer to a memory address that holds this data. And so just like we dereferenced px in order to find out what was stored at that address, we dereference the name of the array and we find out that the value stored there is a 4. And you can do vice versa. Once you get a pointer, you can pretend it's an array. When I say pretend, you can treat them interchangeably. So if you do this, val pointer is a pointer to this array. Then if you print asterisk val pointer, it'll print 4. But if you print, not asterisk, sorry, star val pointer plus 1, it's not going to print 4. It's going to print 7. If you print star val pointer plus 2, it's going to print that 11. Let's play with that just a little bit. Okay, so right above my pause, right down here at the very last thing in your program, let's make an array of floats. Float, FA for float array, is equal to, and let's just put 3 values in it. 3.0, 9.9, 5.5, whatever. Now let's declare a pointer to a float. Float star PFA, a pointer to the float array, is equal to the address of the float array. And I think I've goofed that. I don't think you use the ampersand there. FA is already in effect a pointer because we declared it as an array. So this stores the address of the FA array into a pointer. So if we want, we can get data out of it. Float F1 is equal to the ampersand, PFA. Float F2 is equal to star PFA plus 1. Float F3 is equal to the star PFA plus 2. And if we print those out, we'll see 3.0, 9.9, and 5.5. So C out F1 plus a space plus F2 plus a space. Not pluses, I'm sorry, I'm not doing Java. F1 followed by a space, arrow, arrow. Arrow, arrow, F2, arrow, arrow, space. Arrow, arrow, F3, arrow, arrow, E and D, L. So if we print those out, we're going to see 3.0, 9.9, 5.5. I hope. Not letting me close this. Well, I hope it's still, oh, it's running in the debugger. Alrighty. Alrighty, so it printed 3, 9.9, and 5.5. So what's going on here? If PFA is a pointer to the array itself, then if you add 1 to PFA and print it out, it's a 9.9. If you add 2 to the array and then dereference it to that, you get 5.5. Now there's something hinky going on behind the scenes here. These are not just 1 byte wide. So how can it get to it by saying +1 and +2? It really ought to be +4 because a float is 4 bytes wide. And this ought to be +8 because of but what it's doing is this syntax takes into account the size of that data type. You remember size of, like when we were calculating the size of an array, we want to know how many elements were in it, so we did the size of the entire array divided by a size of a float or a size of an int. This number here is multiplied by the size of that. We just don't see it happening. The compiler takes care of that for us. All right, I think that's enough. Let's stop here. The big takeaway is that pointers refer to memory. If you want to change the value, then you have to dereference that pointer by using a star in front of it. The real reason you use those is so that you can pass them around without passing in the original data, so that if a method or function needs to make a change to it, it can. And it's certainly a lot more efficient to just pass in a pointer, which is just 1 byte of data, than it is to pass in an entire object, which may have, hundreds of pieces of data in it. Not that we have defined objects yet, but we will. Okay, so this will be n. All right. You can drop it into N, and we are done.